Howdy everybody in YouTube land. I'm doing a quick video on a Macintosh portable because I have a ton of Macintosh portable stuff here at the shop that I need to work on. Since I moved out of my house, I don't have a workbench set up anymore, so I have to do everything here at the shop. Now, there's a problem with these machines, and it's the capacitors. And anybody that's familiar with these archaic machines know that the capacitor plague is the biggest issue right now. Now, there's another problem with these. When you recap them, they don't exactly come good. Some of them do, some of them don't, and then people are wondering why, and they're either pitching the boards or whatever. So I had a few of them sent to me to get worked on. Now, here's the thing, okay? You know, when you do a cap job, you have to be careful because otherwise you'll pull the traces up, and you know, and another problem here is the plating has gone through the through hole, and I thought it was connected to an inner plane, but it's not. So that shouldn't be a problem, okay? That technically that should not be a problem. Now, this one, even though the traces are broke, and you might blame the person that did the cap job, but that's not the case here. Actually, the problem is really, really hard to see, and I'm going to teach you a trick here. And this is absolutely vital for the survival of these archaic machines. So what we're going to do is we are going to turn the flashlight on, and I'm going to show you something you need to look for. You know, I'm going to show you something to look for here. You see that? Nah, maybe not. It's washed out. See the trace, or the annular ring above C11? It's transparent. Copper's been eaten away. That's your problem. That's what you have to look for. One more thing. This board here was giving me some grief. Let's see. For one, the problem with this board, it would not produce the correct battery voltage. It would show full all the time, and it wouldn't induce the charger, and sometimes it would show empty all the time and not induce the charger. At first it would be empty, it showed it was dead, or something like that. Anyway, and again, the problem ended up being over here. I had two wires, one of them here, which is actually the pull-up for the reset button. So without this there, because it breaks right at the edge of this cap here, so without that wire, this thing would spontaneously reset if you wanted it to. With that fixed, that went away, but then the battery problem still remained. So I took out the Burns network filter, because the Burns network filter is actually proprietary to Apple. This has an array of different value resistors in there, and this here forms the window comparator for the battery voltage. This is designed if the battery voltage gets low and you have the battery or the charger plugged in, it'll turn on and allow the current to flow through the MOSFET back to the battery, which plugs in here. Okay. Also, this has the intervoltage lockout, so if it falls down to 5.6 volts, it will tell the power management unit. It'll drop to 0 volts on the analog to digital converter, the ADC, and then it'll shut down and go to sleep. Okay. Also, this has 2 op amps in here for a difference engine through this transistor here to determine the voltage level on the analog to digital converter from the battery. Okay. This is the reference. This generates about 1.2 volts for the reference on here. Okay. Up here generates a stable 5 volts from the regulator, which is over here. The reason why you need that 5 volts is that way you have a window that the chip never exceeds, because the battery voltage runs as high as 7.5 volts, sometimes 9, because there's a 9 volt battery that sits here in the carriage. When you have to swap out the battery, if you open the battery lid, the standby will switch over to 9 volts. The machine won't run off of that, of course, but it will switch over to 9 volts. That way you don't lose the contents of memory while you drop in another battery. This ensures that you have a 5 volts, that way you don't overvolt the PMU and burn it out. And this here is the actual comparing voltage. So this op amp actually is the constant, and this one's the varying, and this op amp over here is the actual feedback from the regulator. And this, anyway, so that op amp drives regulator, I mean. And then the fourth one, I forget what it does. I don't think it's used. So anyway, there's the voltage reference, which is pinned here, and then the other one is the comparison of the level. And then the 5 volts up here actually goes to the collector of this transistor. That way it ensures that this transistor, in the base of this transistor, is driven from this op amp. And then the emitter goes all the way through the board, back and around to over to this point right. Hold on, grab my pick tool. This point right here. This little eyelet right there. Actually, underneath the board, that is the analog to digital converter input. And underneath the board is a resistor and a capacitor, that filter, the RC network filter for the ADC. And that is actually not the right thing. That is the pinouts of the Apple custom PMU. And actually, this is a Apple part number that doesn't have anything regarding to a Mitsubishi processor, but that is actually a Mitsubishi M50753, and this is the exact pinout, and the ADC is coming in right here. Okay, the reference voltage is not hooked up, so I'm assuming it's using the internal 5-volt reference. But before I hook this wire up, I'll show you what this thing's doing. So what we'll do is we'll turn it on. We'll go ahead and hook up our ground. We'll hook up our power, and then we're going to hook up our PRAM. So the battery reads full all the time, to reiterate. So what we're going to do is we're going to turn the power supply on 5.6 volts. In theory, that should be the bottom end of the support of the unit. So in theory, the ADC should be seeing 0 volts right now. Well, let's see what we have. So what we're going to do is we're going to probe it right at our point here. Now, look at that. 4 volts. So, and I'm at 5.6. So what we're going to do is we're going to swing up to about, I try to do this one-handed list on 7.5 volts. That's the top voltage. Let's see where we're at now. 5.8. That's a pretty high swing, almost 6 volts. So, but here's the thing, if I can drop this all the way down to say almost 4.7 volts, it shouldn't even see that. Look at my ADC voltage, 3 volts, 3.1 volts. So of course, this thing is always going to register that the battery is full all the time because the ADC is getting a complete value. Then I tried replacing this chip from the other board, which is right here, because this board here is garbage. It gave me a SAD/MAC code of CD37, which indicates that it couldn't communicate with the PMU. So I took the PMU off of this one, put it on this board. It didn't make any difference. I took the Burns network filter and the linear technology op amp, moved them over to this one, and it still did not make any difference. So then I decided to test voltages on this board, and I get a full 0 to 5 volt swing, like I should. So, doing some further testing, I had found a broken connection underneath this chip, which I'll put in a photo in this video so you can see that, which I repaired here. Well, there's also directly under this chip, right about here, there's a through hole that comes to the board, and it goes over to this one right here, okay? Well, it's open from here to here as well. I figured when I jumped it from this point back to this point that it was going to complete the connection because the trace comes through here and over to this hole here. So I figured it was connected, but it wasn't. So I took a meter and tested it, and guess what? It was open. So what we're going to do is I went ahead and attached a wire. So what we're going to do is we are going to attach this new connection back over to here. I'll probably take it back over there. I haven't decided. I'm going to take this new wire and attach it, and then we're going to run this test again and see where we're at. Now, with that repair completed, I went ahead and made a new wire connection over to that point, like there should be. So now what we're going to do is we're going to fire it back up again, 5.1 volts. Now over here should be darn near 0. And it's not. There's still a problem. Nope, she's falling. Nope, she's raising. Well, that didn't work. That did not work at all. Finally got this sucker fixed. Notice I had to make that trace run, which I showed a little bit ago. Still didn't work. But, you see that third capacitor, the one on the right there? I had to replace it. There was a yellow little tantalum there, and it was leaky, electrically leaky. So actually this capacitor electrically connects between these first, or these, well, you know, these two pins right here. Actually, let me see if I can point that out better. Yeah, these two pins right there. It connects electrically between those two, and well, it was leaky, so it was causing this op amp to give out erroneous readings. But the strange thing was, all this cap actually does is this capacitor slows down the rate at which the ADC compensates for the battery voltage. Really, it makes it raise really long or fall really long. It adds a time constant, a delay. That way, the reason why they did that is if the Mac is, you know, fluctuating power consumption wise, the voltage is going to jump up and down a bit on the battery. So instead of having your battery meter do this all the time, well, it keeps it pretty steady. So what I did is I removed that, and it worked. You know, there was no more, the voltage wasn't bouncing all over the place. So that was a good thing. So I decided to say, okay, I pulled it out. So I stole one off of this board here and stuck it on there. No more problems. It's worked fine ever since. So I had all hooked up, had the screen hooked up, hard drive hooked up, had everything going, and was, you know, dialing the voltage up and down, and was watching the meter because I had the desk accessory up. I was watching the meter fall, say it was in reserve power, and I could raise it, bounce it up. So I left it about halfway, which is roughly around 6.2 volts. Left it halfway and let it sit there for 15 minutes and never had any more problems. So I can finally call this one fixed. Then there's the matter of the third one that I can't seem to figure out. This one will not post, it will not chime, it won't do anything. And if you noticed, I pulled all of the chips off. And actually, this board here, the one I was just showing you, you may not be able to see it, but you can probably tell, I soldered all of these chips on. So what I did was I actually took all the chips off of here and I moved them over here. And this board still worked, and this board did not. So that rules out the chips. The only chips I didn't swap, now I took these two out, but the only ones I didn't swap was these three and this one. I did swap that one. And the keyboard controller, which I know it's not bad. So, you know, oh, and I swapped all of these out, which is the RAM decode logic, the timing controller for the DRAM and ROM and all that fun stuff, and it still did not work. So then I decided to give up on this thing. Actually, that's where I stole the capacitor from. So I decided to give up on this thing and grab another one. This one is a non-backlit version, which has a little hybrid module over here, and see the cap damage pretty badly. And I hooked this one up. I checked, you know, traces. I took the VL off. I checked traces and all that fun stuff. And guess what? This one does the same exact thing. Identically. Okay? It's the same exact thing. It does not chime. It doesn't do anything. It turns on. That's it. So then I decided to probe 3 lines right here. Okay? Which is, one is the bus error, reset, and halt. Well, halt, there's a pulse train, a pretty good negative going pulse train, which is identical to what's on reset. Bus error, there's 3 negative going pulses, and then there's a pause for a while on the scope. So you'll have a pulse, you know, you'll have a steady line for a while, then 3 little pulses like this, you know, and then it'll go steady for a while. And the pulse is real narrow, so it's probably only 1 bus width wide. I don't have a logic analyzer, so I couldn't tell you. I need to get one of those. So I decided to figure that out. So my guess is this thing is stripping a bus error. And why it's tripping a bus error, I have no clue, but it is. And I decided to check these logic circuits here because these are the closest to the capacitors that leak. And this is the schematic I came up with that, which means there's no breaks. You know, and this all this really does is there's the lower address or loader data strobe, and it goes off. If you see the star one goes off to here, which is actually this pin right here, and that overlays D0 through D7 on top of D8 through D15. So it's like it makes the word a single byte. You know, that's all that does. But that wouldn't stop it from booting. Well, it would, but I was watching this while it was booting on the good one and the bad one, and it stays off unless RAM is being called. Well, the crash happens before RAM, so that's not the issue. These are the data buffers for the RAM and ROM. Actually, no, the ROM is directly connected to the CPU, but these are the data buffers for the RAM. Check those over to the processor, they're all good. And these are the address buffers, and they're tied low, so these buffers are on all the time. So the address lines come over here through the buffers, and then they go over here. And I tested those, and they're good as well. There's 47 ohm resistors underneath, but they're good. So the system can see ROM. Now that doesn't necessarily mean that the select lines aren't bad from here on out, but I know this chip isn't bad because I've already been through that with this one, and it didn't make any difference. So something was throwing the bus error, and I don't know what it is. So what I was going to do today is actually, I drew that schematic out. So what I'm going to do now is take the good one. I'm going to shrink this processor down and print it out so I can actually take measurements. So I was going to check to see where these go to both glues. So I was going to take address 1, check it on this glue and this glue, address 2, this glue, address 3, this glue, this glue. You see where I'm going? That way I can figure out where they all go between the glues. Then I will do the same thing, address 1, 2, 3, 4, and I'll check to see where they go here, here, and here. And I'm going to mark them down in like slash, you know, glue 1 slash glue 2 slash SEC slash, you know, just that way I have a little indication for each and every pin where they go. And then what I'm going to do is I'm going to take the leftover pins that didn't go to the processor, and then I'm going to take those leftover pins and I want to measure where they go here. So all the peripherals through the logic circuits and stuff. You know, I want to measure where they go. Do they connect here directly to here, here directly to here, which they do. I know that for a fact, and that way I can build a secondary table, and then where they go over here. You know, that way I can essentially create a logic map where everything goes. I don't care where this stuff goes to here and interconnects between each other, because that's not my problem. My problem is this main logic system cannot access ROM correctly, or cannot access something correctly on the system bus. And I've been through traces and stuff like that, because this is where the capacitor sits. So anywhere in here is going to be ground zero for corrosion and anything breaking. If these break, that would stop it from starting, because that's the buffers for the ROM and RAM, which I checked that and I didn't see any breaks there. This circuit here, like I said, is part of the lower data strobe and modem controls. So when you plug a modem in and it wants to use sound, these logic circuits switch around to pipe the modem audio directly into the sound chip. That's all these do. And and the PMU can turn the sound on and off through, and these chips buffer that data, but that's it. These 4 control the backlight, which is not present on the other one. That's the video RAM, and I'm not worried about that. And this is the keyboard controller. This is the clock oscillator for the SCC. So that's where I stand at this point. I'll figure I'll go ahead and upload this video now, and that way you can get an idea of what I've been doing. So, before I do, hold on, one more thing. I keep forgetting about this board. This is the first board I worked on, and I repaired it. It had a bunch of open V as I showed earlier. When I had the flashlight showing through where it showed the bad through holes, well, I went ahead and repaired the connections. I found one there, and the other several wires of broken traces are under there. There's one more over there, and there's a lot of those traces eaten away, but these were clearly visible. You couldn't see them, or you couldn't miss them. They were clearly visible, unlike this one, which actually, if you could tell, they're made from different manufacturers. So this board, you could tell where the damages was. This particular board, you cannot. So I went ahead and fixed this one, and it actually worked first try. I didn't have any problems. So thank God for that, at least. And then now this one's working again. And this was my last one, but before I ship this guy back out, I want to do the the CPU to these three and create a chart, and then the leftover pins from here, and here, I want to see where else they go. Because as well as I do, all these chips are tied on the same address and data bus, but the chip select lines and the upper address bits are going to be decoded by the glues. So anyway, thank you for watching.